In the previous video, we covered how to train YOLO models on a computer. This time, we'll explain how to deploy the YOLO v5 model on a virtual machine and an OrangePi. Following the approach outlined at the end of the last video, we obtained an ONNX model. Using the same Ubuntu virtual machine, we'll convert the ONNX model into an RKNN model. Then we'll deploy this model on the OrangePi. The virtual machine version we're using here is still the same 22.04 version. You can download the RKNN 2 file from the video link or the RKNN GitHub official website. Next, open the packages folder. Here, we'll use the terminal to open it. First, use ls to list the file names. You can see there are two types of files here. One is dependency packages ending with .txt, and the other is binary packages ending with .whl. Both can be installed using pip install. You should choose the appropriate version based on your Python environment. For example, I'm using Python 3.10, so I'll select CP310 for installation. You can see the download has started. Since the installation package is quite large, it may take some time to download. Please be patient. After downloading this, install the WHL file using the same method. Here I'm still selecting the Python 3.10 version. Once all these are installed, we can open Python and enter this line of code. For a simple verification, if no errors occur, it confirms our environment is set up correctly. Now back to the computer, we'll send the previously trained ONNX model to our virtual machine. Then retrieve an image from the original dataset and send it to the virtual machine too. In the virtual machine, save this file to this directory. You'll notice there are quite a few files here, but the link we provided doesn't contain all these files. So don't be surprised if the files in your downloaded link are fewer. Rename the file to bus.jpg and save it. Of course, you don't have to use this exact name. We'll adjust the code later. Next, open this YOLO v5 file in this folder. Line 11 specifies the ONNX model name we need to import. The next line defines the RKNN model name for export. The subsequent image_path is where we place the image for testing. Our bus.jpg file. Note that all these files currently share the same directory as test.py. If you move files to another folder, you must update their paths accordingly. The classes here also need to be modified to match the object categories we want to recognize. Since we're identifying numbers, enter these digits here. One more thing to add, depending on the chip used in the OrangePi, we need to adjust these parameters. For example, I'm using an OrangePi 5P, so here it's RK3588. If using a 3B or similar model, it might be RK3566. No other changes are needed elsewhere. Then run it directly. You can see the final output. Here it recognized 1 and 2, with confidence levels of 0.89 and 0.81. We can also find this result.jpg in this folder. This is the image just exported. You can see 1 and 2 were accurately recognized. The generated RKNN model is also here. Send this model to the OrangePi. Then the work on the virtual machine is complete. Now let's look at the OrangePi side. First, download the compressed package from our link. Here we also need to set up the RKNN environment for the OrangePi. It's right here. Open the terminal. Use the unzip command to extract it. After extraction completes, open the folder named RKNN 2. Inside, locate the RKNN_toolkit-lite2 folder. Open Packages. This contains the environment required for the RKNN model on the OrangePi board. My Python environment on the OrangePi is also 3.10, so I'll directly install the 3.10 version package using pip install. Let's fast forward through the installation process. Generally, the OrangePi comes with an older version of the RKNN driver. It needs to be upgraded. Now, go back to the previous menu. Locate the file named RKNPU2. Click on the Runtime option here. Select the Linux file, then choose the first folder here. The OrangePi architecture is Arch64. Therefore, we select this Arch64 file. We need to place this file in our system directory. Open the terminal. We need to copy this file to the /usr/lib location. Remember to use sudo for administrator privileges when copying. Return to the RKNN server directory. Again, select the Arch64 option. We also need to copy these 3 files to our system directory. Specifically, copy them to the user/bin folder. Here, I sequentially copy each of these 3 files, one by one into user/bin. Now, navigate to usr/bin to locate the files we just copied. And run the script file we just copied. After running it, our RKNN driver will upgrade correctly. So, open your terminal in the usr/bin folder. First, use the chmod command to change the permissions of this script file. I'm changing the permissions for all 3 files at once. Run the restart_rknn.sh script directly. In short, once you've done this, the OrangePi environment is set up. Let's open pycharm on the OrangePi. Here's a prepared detect.py file for you. Earlier in the virtual machine, we demonstrated how to recognize an image. Now on the OrangePi, let's identify the real-time footage captured by the camera. First, download the required packages for the environment. The packages needed in the code can be installed with these commands. Let's run it first to see the results. This model can accurately recognize all 10 digits from 0 to 9. This is an older model I built. It runs at around 20 frames per second, which is sufficient for competitions. If viewership increases later, I'll teach you how to optimize the model. So make sure to watch the videos and hit the triple tap. Let's terminate the model here and examine its internal parameters. We placed all files in the same directory as the .py file. Subsequent files use relative paths based on this location. The first is the path to our model file. The second is the name of the image we need to detect. But we won't use it in this demo, because I'm using video captured from a camera for recognition. The categories here are our 10 digits, 0 to 9. Let's focus on these 2 parameters. The first parameter, starting with obj, represents the confidence threshold for recognizing objects. For example, this value is currently 0.8. If the model predicts an object with confidence below this threshold, we discard it. If the predicted value exceeds this threshold, we retain it as the target object. Based on my testing, 0.8 yields good results. Now let's observe what happens when this value is too high or too low. Here we see a value of 0.99. Notice that in this image, no objects are detected at all. Now I've set it extremely low at 0.05. We find it easily detects irrelevant objects. The second parameter is NMS, non-maximum suppression, threshold. Simply put, we don't want a single object detected multiple times. This parameter prevents that. If 2 detection boxes overlap excessively, exceeding this threshold, the 2 boxes will merge. A value set too low causes multiple detections, resulting in ghosting, like what we see here. In short, you'll need to fine-tune these 2 parameters yourself. The final adjustment is the camera ID here. Mine is 21. Yours will likely be different. Most commonly 0 or 1. If you're unsure, search online for how to find your camera ID. An incorrect ID will cause the camera to be unrecognized, triggering this error. Once configured, it should run directly, producing the effect demonstrated earlier.